Okay, so covalent bonding. So we know that covalent bonding is sharing of electrons, right? Because we've talked about that. You guys are feeling it, right? You understand that concept of sharing? If I remember correctly, we talked about the two different types of sharing. I told you about my sisters.
Yeah.
Weakest in the middle.
The weakest in the middle. But you guys are remembering a lot. Yeah, we put the weakest in the middle. God, you guys learned a lot here. So we know that the guy who has the weakest electronegativity is always going to be in the middle. So we're going to be talking a lot about electronegativity today. Okay. So there's a couple of things that I want to make sure that you guys understand about that covalent bond. Covalent bond is sharing of electrons. So when we say sharing, let me kind of give you an idea what it is. Okay. So the electron is orbiting the nucleus, right? And we've already talked about that. We talked about that in chapter 11. Now, when it's orbiting the nucleus, it's going around and it's making what we call an electron cloud, or what they call charge density, right? And so that means that basically the electron is constantly moving, but it occupies the space that it's moving, okay? So since this electron cloud is being made for one atom, right? All the electrons are orbiting, and there's an electron cloud of the other atom, stuff all the electrons orbiting. So when they're sharing electrons, their electron clouds are going to be overlapping, okay? But it's only for that element that's being shared and also that orbital, okay? Does that make sense? Or I should say, at least that's what they believed initially, okay? Are you with me so far? You got to speak up or forever hold your peace. Okay,
Yeah,
so if you
okay.
don't see it, don't worry about it. I'm going to show you a picture, okay? So here, this is one hydrogen atom, okay? Here's another hydrogen atom. But it always gets on me about this. I don't spotlight it. Hydrogen atom, right? Hydrogen atom here, hydrogen atom. Okay, hydrogen has one valence electron. Is that true?
Yes.
Okay.
Yeah.
So if we have one hydrogen atom and one hydrogen atom, and they come together and they form that covalent bond, then this is what you have, right? And so the electron is literally orbiting both of those nucleus, right? So it's being shared evenly between the nucleus. So both this electron is orbiting it, both, and this electron is orbiting. Okay, so that means that they're sharing. Okay, so that's what we mean by sharing. And so we depict this to kind of make it simple for us, our mind. We depict this as bonding, right? As the bond. So we draw it out like this, right? We have that one electron. This guy has that one electron, and then when they come together, they share those two electrons. Okay, simple. Okay, so we use Lewis dot structure to help us understand that concept of bonding. And that's what Lewis structure is for, to help us understand that there's covalent bonding happening. And we're going to use those Lewis dot structures to sit there and show that covalent bonding is happening. Okay, so we know that bonding is only going to be done with those valence electrons. What are valence electrons again?
Those are the electrons that are in the outermost shell.
Those are the electrons that are in the outermost shell that can be used for bonding, okay? So, because you're not going to use the one that's in the core because they're already occupied, they're happy, they're stable. You don't want to mess with something that's already good, right? You've heard that story or that saying? If it ain't broken, don't fix it, right? You've heard that before? Right? So you don't want to mess up something that's already good. So you want to leave those guys alone. And you only want to use those ones that are kind of like, you know, out there, out on their own, you know? And those are the ones that you're going to be using for bonding, okay? So if we have fluorine, how many valence electrons does fluorine have?
7.
Fluorine has 7 valence electrons. So we put our 7 dots around it. And we know that fluorine, because you guys remember your diatomics? Have no fear of ice cold beer. What are your for diatomics?
Hydrogen.
Hydrogen. I heard oxygen.
Fluorine.
Fluorine.
Oxygen.
Chlorine.
Chlorine. I thought I heard somebody say nitrogen.
Nitrogen.
Bromine and iodine.
Yes.
Okay. So have no fear of ice cold beer. Easiest way to remember. So we know that anytime you have that term gas, hydrogen gas, we know it's H2. Anytime we're talking about fluorine gas, we know that it's F2. So in this case, we're talking about F2. So both of these guys have 7 valence electrons. Okay, so how many electrons are they going to share to reach what we call their octet?
2.
2. No.
A single bond.
It's going to be a single bond, so they're going to share 2 electrons at 2. So if we do that, because we know that each one has how many?
2, 3.
7, right? So that's 7 plus 7. That should be 14 electrons that we're working with. So that's 2, that's 4, that's 6, that's 8, that's 10, that's 12, that's 14. We know that this line represents 2 electrons. Okay?
Dr. Henry,
Yes.
there's some questions on the test where it has like a thicker line. What does that mean?
Wedge and dash one?
No, it's just like it's like a straight line, but it's just thicker than the other one.
It's bold.
Yeah, like a
It-
bold line.
Oh, the bond?
It still represents a bond. It doesn't mean that it's anything different. It's just that probably the formatting of the, so when I put in Canvas, the formatting gets screwed up. So,
No, it's on the practice test.
okay, so I have to take a look at that. It's not
Okay.
in Canvas on the practice test.
Yeah.
No, it's just on the practice test. When you open it up, it has questions about like this compound, which bond represents it the best, and then
Uh-huh.
it'll show a bunch of bonds. And there's somewhere it has like a thin line, like the one you drew, and then right above it, it'll look like a double bond, like as if you drew 2 lines, but one of them will be like way thicker,
Okay, so it'll be like this.
and then like but then one of those is like extra thick. Yeah.
It's probably, like I said, it's the formatting. So it's not able to make that line. So like a triple bond, a lot of times when we try to make a triple bond, it has to be drawn differently. And so it's not making the line right.
So would that mean a triple bond then?
So it would be a triple bond would be a triple bond.
Okay.
But sometimes you'll just have one of the lines will be thicker than the other.
Oh, but it doesn't mean anything.
No, it doesn't mean anything.
All right. Sorry, I know we're not supposed to ask questions. My bad.
No. You can ask questions about the thing, but we'll get to, I'll try to answer them along the way. It's okay. Ask questions about what we're talking about, and then ask me all the questions that you got. That's fine. Still ask questions. Okay. So
6, 2, 6.
okay, so we want to make sure that we reach the octet. Everybody reaches his octet. Okay, so in this case, we count the number of electrons around fluorine. That's 2, that's 4, that's 6, and this line counts as 2, right? So that's a total of 8. This guy is 2, 4, 6, 8. Okay, does that make sense?
Yes.
Okay, so that is Lewis structures. And that's what you guys have to do a lot of. If I can get my thing to, okay, my slideshow is not working. Okay, so okay, for some reason I can't get my slideshow to work. Okay, there we go. Okay, so let's talk a little bit more. Oh, let me go back. Okay, so we know that this here represents the shared electrons. Those are called like our bonding electrons. These here are called our lone pairs, right? So fluorine has 3 lone pair. When we're talking about all the electrons, we call them the lone pair electrons. That means I want to know all of the ones that are there. So I would say, how many lone pair electrons are around fluorine? You tell me how many.
6.
6. Okay. If I said, how many lone pair are around fluorine?
3.
3.
6.
Okay, there are 3 lone pair, but there are 6 lone pair electrons. Let me write that out. So, because pair, we think about a pair of shoes. That's 2, right? So that's 1, 2, 3 lone pair. Okay. And then if I ask you lone pair electrons, I want to know all the electrons that are around. Okay, does that make sense? Do you see the distinction between it? So fluorine has 3 lone pair, and it has 6 lone pair electrons. Okay, now, why is this important? Because we do something called formal charges. Formal charges allows us to sit there and figure out how stable molecules are. The way that we calculate formal charges, and I mentioned this during our lab, it's going to be the number of valence electrons of that atom minus the number of lone pair electrons minus the number of bonds. Okay, so if we're calculating the formal charge for this guy, oh, and I should tell you this. The goal is to make sure that your formal charge is equal. You want it to equal 0 if you can get it to, or as close to 0 as possible. Okay, so if we take fluorine here, so you take each atom independently. These are both fluorine, so they're the same thing. So they're going to have pretty much the same formal charge. So if I was calculating the formal charge of fluorine, how many valence electrons does fluorine have?
7.
How many lone pair electrons?
6.
How many bonds?
1.
Okay. So 7 minus 6 minus 1.
0.
0.
Okay. So it's 0. That means this is a good bond. It's a stable bond. Okay. So the formal charges helps us understand whether or not our Lewis structure is going to be a stable Lewis structure or is it going to be a crappy Lewis structure. Sometimes you have no choice but to go with crappy Lewis structure. Okay. I'll show you an example of that in a second. Okay, are you guys good so far?
Yes.
So far, yeah.
Okay, so let's see if we can make it a little bit harder. Oops. Okay, so if we have CO2, right? We know that carbon has how many lone pair?
2.
I'm sorry, not lone pair. Carbon has how many, take a step back. How many valence electrons? I got ahead of myself.
4.
Carbon has 4 valence electrons. Oxygen has how many valence electrons?
6.
Times 2,
12.
because there's 2 carbon, 2 oxygens.
Wow.
So that's a total of 12. 12 plus 4.
16.
So I have 16 electrons to work with. Okay. Now, we've already talked about electronegativity. You guys should be somewhat familiar with it. We spent a little bit of time last time talking about electronegativity. Right? You guys know that you can go on peak table, you could click on electronegativity, and it'll give you the electronegativity table. Right? So you guys can kind of utilize that. Man, I wish there was a peak table when I was in college. Man. Okay, sorry. So who's going to be in the middle?
Carbon.
Carbon.
Hey, Sal, why is carbon going to be in the middle?
It's the smallest,
Smallest
the
in what?
weakest.
Weakest. Weakest in what?
Electronegativity.
It is weakest in electronegativity, right? So that means that oxygen is going to have more pull. It's going to want to pull more than carbon. Okay, so we know that carbon is going to be put in the middle. And I also told you guys that carbon was.
Carbon can bond with a lot of others.
Carbon's a whore, basically. Carbon can have 4 attachments, right? It can attach to at least 4 things. So that's one of the reasons why carbon likes to be in the middle. That's also part of the reason why carbon is the center of life. You guys know that carbon is the center of life, right? So carbon has the ability of having multiple attachments because it needs 4 electrons, right? So, best case scenario, it could have 4 different, gentlemen callers or female callers, depending on who carbon is, right? So, or it could have 2, So carbon is flexible in a sense. It has that flexibility because it needs those 4 electrons. And so it's willing to sit there and be kind of pushed around. It's not as strong. It's accommodating, okay? So it will be in the middle, okay? So I always remember, and it's bad, and it is what it is. Carbon's a horror. Carbon's gonna be in the middle, right? Because it's easy for me to sit there and remember. So I know that if I have carbon there, carbon is gonna probably be my center atom, okay? So we know that carbon is gonna be that center atom because of electronegativity. It's not gonna have that pull compared to oxygen, right? And we also know that carbon kind of likes to be in the middle, okay? So let's put carbon in the middle. It has 4 valence electrons. So we put the 4 electrons around it. Oxygen has how many valence electrons?
6.
Okay, so that would give me my 6 around it. Now, the goal is we're trying to make everybody happy, right? And to be stable, you need to have 8 electrons around you. So you want to try to set it up so that they're sharing in a way that everybody has 8 electrons. That 8 electrons means that they're reaching their octet. Oct, like octopus, 8 arms. Octet, the octet rule means you have 8 electrons around you. So you move things so that you end up with everybody having 8 around them, if you can get 8 around them, okay? So is there 8 around this carbon right
No.
No.
Somebody say,
No.
No.
okay, so since there isn't 8 around them, we're gonna sit there and move electrons because we know that electrons move, right? Since we know that electrons move, it's okay for us to sit there and move them. So if we move a set of electrons here, that's gonna give us 6, that's gonna be, right? Around carbon. That's not enough, is it?
No.
Okay. If I move another set of electrons here, then that means how many are going to be shared?
8.
8. Okay, so let's go ahead and make that structure. Do it in red. Okay, so right now, carbon has 8 around it. How many does oxygen have around it?
8.
And this oxygen?
8.
8.
So this is a good structure. So the easier way to draw this is by drawing it with a line, because sometimes dots get lost, particularly on Zoom. Okay. So this would be a double bond. When 4 electrons are being shared, that's going to make a double bond. Okay. So everybody's happy, their octet rule is satisfied. Okay. So this is considered to be one form that we could use. We could have also done it differently. I'm going to go back to our original structure here. So I could have took both bonds or both lone pair from this oxygen and did something like this. Where we would have a triple bond. Now, according to the octet rule, this is fine, right? Everybody has 8 around them. That's 2, 4, 6, 8 around this oxygen. That's 2, 4, 6, 8 around the carbon. That's 2, 4, 6, 8 around this oxygen, right? So according to the Octet rule, perfectly fine, okay? However, if we looked at formal charges, so this is going to be our first oxygen. This is going to be our second oxygen. Okay. So for O1, what is going to be the formal charge? So how do I calculate formal charges again?
Valence electrons minus lone pair electrons, and then minus the number of bonds.
Okay. So valence electrons minus lone pair electrons minus the number of bonds. So how many valence electrons does oxygen have?
6.
How many lone pair electrons?
2, 1,
2.
Right here. Lone pair electrons.
2.
2,
And how many bonds?
3.
3,
Okay. So we do the math. 6 minus 2 minus 3.
1,
So that equals a positive 1, right? Okay. Carbon. How many valence electrons does carbon have?
6.
4,
Carbon has 4 valence electrons.
Yeah.
How many lone pair electrons?
0,
0. And then how many bonds?
4,
4.
Okay, so that's beautiful. Nice 0 number, right? Okay, for that second oxygen. How many valence electrons does oxygen have?
6.
How many lone pair electrons?
6.
yes,
1, 2,
And then how many bonds?
1.
1,
So now I'm going to also tell you one other thing that I forgot to mention. When we add up the total of the formal charges, it should always add up to 0 if there's no charge on that compound. But if there's a charge, it should add up to that charge. Okay. So carbon dioxide doesn't have a charge on here, so it should always add up to 0. Okay. So if we do this, the formal charge for this. So we'll say this is oxygen 4. Oops. Say 3 and 4. So we can compare our structures here. Okay. So for oxygen 3 and 4 are essentially going to be the same. So 3 and 4 are going to be the same. The formal charge will be. Okay. So how many valence electrons? Oxygen.
6.
6,
How many lone pair electrons are on this oxygen? Number 3.
4.
And how many bonds?
2.
2,
So that equals 0. And then what about our carbon?
4,
4.
4 valence electrons. How many lone pair?
0.
0,
And 4.
4,
Okay. You guys see that? Okay. So remember, the goal is to be close to 0. Possible. Which structure is the closest to 0?
The first structure.
Okay. So this guy is the closest to 0. Actually, it's at 0. It's perfect. So this would be the more stable structure. Again, formal charges, this guy is more stable. But according to the octet rule, either one would have been fine. Does that make sense?
Yes.
And
Yes.
do you see the distinction and why we use the formal charge at points?
Yes.
Okay.
I have a quick question, Dr. Henry. So like on the exam, how would it be worded? Would it be just like how you have it, find the formal charge for this compound, or?
So I teach you guys formal charges because I talk about it in the homework. And then a lot of you guys are going to be going into higher levels of chemistry. You have to do organic chemistry. You're going to have to do, and most of you guys are going to have to do organic chemistry or intro to organic. And then you also have to do, some of you guys are going to go into Gen Chem, general chemistry. Or you're going to end up getting another chemistry class when you go into your nursing program, right? And so I teach it to you now because you're going to be exposed to it later on. It's not required for this course. So I teach it to you so that you know it. And so you'll be familiar with it. And so when you see it in the future, you'll be prepared. But on the exam, I typically just ask you Octet.
Okay.
Yeah. And so if I do make a distinction, I will say, according to the Octet rule or according to formal charges.
Okay.
Okay.
Thank you.
Okay. So let's see. Simple. That wasn't too hard? Okay, so let's do something that is hard, right? Because we've talked about ions, right? We're familiar with ions? So I'm going to kind of introduce you to a term called polyatomic ions. Can I erase these?
Yes.
Okay. Okay, so this is called a polyatomic ion. Poly meaning many, right? Or multiple, and then atomic, atoms, ion. So it's many atoms that make up this ion, okay? So in this case, we have these guys that are going to be covalently bonded together to form an ion. This lets me know that this ion has 2 extra electrons added to it. So when we draw the structure, we have to take into account that there's going to be 2 extra electrons, okay? Because that's what the 2 minus means, right?
Mm-hmm.
Okay, so who's going to be the center atom? I don't know it off the top of my head. Actually, I do know it off the top of my head. But let's go ahead to P table. Get it up. Come on. Apologize, things are just not running fast today. Okay, can you guys see my P table?
Yes.
Okay, so we go to electronegativity, we click on that, and that gives me the electronegativity scale. Okay, so this lets me know what the electronegativity looks like. So we're looking at SO4. So where's S?
Under oxygen.
Under oxygen. Okay, so here's our sulfur. Right. So sulfur's electronegativity is 2.58. Oxygen's electronegativity is 3.44. Who's going to be in the middle?
Sulfur.
Okay, so we're going to put sulfur in the middle. Okay, so we're going to put sulfur in the middle. Okay, so let's see. Sulfur has how many valence electrons?
6.
Oxygen has how many valence electrons?
Also 6.
And there's 4 oxygens.
4.
4. Okay, so this here, let me see, different color. That number there means what? Again,
An extra 2 electrons.
an extra 2 electrons. So we're adding an extra 2 electrons here. 2 electrons. So 2. So if we add these together, 4 plus 24 plus 2.
32.
So we have 32 electrons to work with. Okay. So we want to put our electrons around the sulfur. It has 6. We know that there's 2 extra, so let's go ahead and put those in the middle because it's easier to take them in the middle and move them where we need to move them to, if we need to. So those are those extra 2. And then we have 4 oxygens. And how many valence electrons does oxygen have again?
6.
Okay, so can we place this so that everybody's octet is reached? Or fix this so that everybody's octet is reached?
It already looks like they all have an octet.
Okay,
Make it a single bond all the way around the S, right?
okay, so you're just saying 4 single bonds.
Yeah. Because they won't share the electrons without a bond, right?
That's right. Well, when you put them between them, it's kind of understood that they're sharing, but it's better to show it with the line. It makes it clear for, teachers like me. We're old and do they understand that they're sharing? Okay. And grouchy. Okay, so we want to count to make sure that we have all of our electrons. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, is everybody's octet reached?
Yes.
Okay, and then the last thing what we would do, since this is an ion, we would put brackets around it to remind us that this is an ion, and we remind us that we added 2 electrons to it by putting the -2 charge. Okay. Now, if we looked at the formal charges, the formal charges would not be happy. Let's look solely at the sulfur. Sulfur has how many valence electrons?
6.
So I'm going to say Fc for formal charge. So sulfur has 6 valence electrons. How many bonds? How many lone pair electrons?
0,
And how many bonds?
4.
And then our oxygens, these are going to be all the same. So valence electrons,
6.
how many lone pair electrons?
6.
And how many bonds?
4.
You mean 1? Because we're looking at 1 oxygen independently, right?
Okay.
Okay, so that would be a -1. Okay, and then the other oxygens would all be exactly the same. And so if we added the charges would add up to -2 because you had 4 oxygens that would have a -1, -1, and a -1. Okay, so then we add them up, it should be a -2 charge, -1, -1, -1, -1, plus 2. So that's a -2, right? That'll be the charge that we have. Okay, so is 2 close to 0? Yes, no, maybe? Yes?
Well, it's not 0, but it's close.
That depends what question you're asking.
So it depends on my
Closer than
question.
5.
Yeah. You know,
Okay.
how many times have you been arrested? 2? Well, that's a lot.
Okay, I get it. Let me rephrase the question. Okay, so do you think we can get closer to 0 if we make some changes?
Well, if you do any kind of double bonds, you'd still need a bond. I don't think you can do double bonds with sulfur and oxygen, 4 of them.
Okay, so this brings up that question about that octet rule. This also brings up a question about exceptions. Okay, so let me talk to you about some exceptions. Okay, actually, I'll say the exceptions. So we're going to look at this guy again a little bit later. So you guys, you have it all written down. Everybody has it saved.
Yes.
Okay.
I have a quick question. So anytime there's an ion, once we complete the Lewis dot structure, do we have to put the brackets around it?
Yes. 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 If
Yeah.
it's a positive ion, or if it's a negative ion. Yes. Okay. Questions? Any other questions? That's actually a good question, though. Yes. So anytime that there's an ion, you want to put the brackets around it. That lets us know that it's an ion. Okay. Okay, so we've talked about lone pair. We've talked about the octet rule. Okay, you guys feeling pretty comfortable with the octet rule?
Yeah.
Yes.
A little iffy. At least I'm a little iffy.
So why are you feeling a little iffy?
Like just the constant trying to keep it in my head. I think I just need to review it, reread it a bunch of times.
8 electrons around something. So you want to shift things so that everybody has 8 electrons around them, except for who? So far that we've talked about?
Well, the part.
Hydrogen.
Oh, go ahead. Sorry.
I heard somebody say it.
Hydrogen.
Hydrogen, right? Because hydrogen only needs how many around it?
1.
It only needs 1?
2.
It needs 2 because it wants to be like who?
Like
Helium.
Like helium, right? Because helium is that first noble gas that hydrogen wants to be around, like. And helium only has 2 electrons around. Does that make sense?
yeah, makes more sense.
Okay.
The part that I'm struggling with, Dr. Henry, is like, say you have an element that has 5 valence electrons, and then say you have an element that has like 7, or
Uh-huh.
something that isn't
So
nice.
you're saying something like NF.
Yeah, you know, and then how do you get an octet out of something that where one has like 5 and one has like 4,
7.
7, or something weird? Yeah.
Okay. So here we have 5 and 7. So if we were putting these together, 5 plus 7 equals 12. So we have 12 electrons to work with.
Right.
Okay. So we would have to share, in this case, another set of electrons.
Right. So you could just move electrons from one element to another element like that.
That's right, because electrons are mobile, right? Especially the valence. And all you're doing, you're just overlapping those orbitals. with each
Diagram or
other.
something.
What was that?
Like a Venn diagram.
Yeah, like a Venn diagram, exactly.
Okay.
Okay, so, but you got to remember, electrons are always moving, right? So when you overlap them, if you're overlapping those 2 orbitals together, so that means that they're sharing. That means that they're able to go around both of them. Okay, so technically, these electrons, if they need to, they can go around the nitrogen if they need to.
Okay.
Okay, that's the reason why they're in that outer shell and they're able to sit there and be used, right?
Yeah.
And that's the reason why you're not using the core, because you don't have access to them. They're kind of locked off.
Okay. Yeah, that's the part I was confused about, is just like if one has 5, how do I give it an extra 3 if I can only bond like 2 at a time? So
Yeah.
that's what I was confused about. Thank you.
Yes. Yeah. So it's, remember, they're the electrons. I know we draw them static because that's the only way we can draw them right now. But really, they're constantly moving. So they're able to sit there and move, sit there and accommodate that bonding. Okay. Okay. Okay, so let's talk about polar and nonpolar. We've already talked about this. I gave you the example of me sharing the toy with my sister, right? So when we're uneven sharing, right, that means that it's polar. When we're even sharing, that means that it's nonpolar. Okay, so if we're sharing in a way that, I think I used water. So oxygen is stronger than hydrogen. So the electrons are they're spending more time around. The electrons are spending more time around around the oxygen than hydrogen. Okay, so since that's the case, this guy is going to be what we call partially negative charged. That means that it has electrons around it the majority of the time. And if this is going to be partially negative charge, this guy is going to be partially positive charge. Does that make sense? Yes, no, maybe?
Yeah, I kind of see it.
Anyone else? Everybody else? You guys don't get it? Or you get it?
I get it.
Yeah.
Get it.
Yeah.
Okay.
Yeah,
Okay.
do it a little slower.
Okay, so let's see if we can do this again. Let's see if I can explain this another way. Okay, so I gave you guys yesterday the example of me and my sister. Right? And I like using this example because I don't like how things work in here. So the electron is kind of like the atomic, in my case. Okay, so we're told that we have to share this. So I get it 90% of the time. My sisters get it 10% of the time. Okay. Are we sharing? Brianna, are we sharing?
Technically, yes. That's
Yeah.
right. I remember the Atari, the loophole.
Yes. So technically, yes. Yeah, I'm looking for that loophole, right? Because I want to play with it majority of the time. I'm the oldest. I'm the biggest. I can sit there and bully my sisters, but they get to play with it still, right? Isn't that the way it works in everybody's household? Brianna, are you with me?
Yeah.
Yeah. Okay. So that's an example of polar, right? Because I'm getting it the majority of the time. Now that's the same thing that happens with the electron. The electron is being shared between the two, but oxygen is like saying, hey, dude, I'm bigger than you. I'm stronger than you. It's mine 90% of the time. You get to still play with it, but it's mine. Okay. For right now, it's mine. You can only get it for that much time. We're sharing, and you get to reach your octet, you get to be like helium, but really it's going to be around me majority. Okay. So that's what's happening in that context. So that's polar, right? That means that the electron is favoring one side or the other. Okay. Another analogy, just another analogy. How many of you guys are married or were married? You are, congratulations, to those are. Okay, now let's say that I was married and I have a kid with my partner, right? And my kid spends, 5 days of the week with my partner and 2 days of the week with me. Now, are we sharing?
Yes.
Yeah, so according to court order, we both get to spend time with the kids, right?
Mm-hmm.
Is it even sharing?
No.
No.
Okay, so that is another example, right? So then that means that it's polar, right? So we have a polar type of relationship. Okay, Does that help the situation? Do you kind of make that clear?
Yeah.
Now, if we had a non-polar type of relationship, we would be sharing evenly, right?
Mhm.
You know, half the year, the kids would be with me. The other half of the year, the kids would be with their mom. So would that be non-polar, right? That's sharing, and that's sharing evenly. Okay, Jane, does that help?
Yeah.
Yeah. Okay, so that's polarity. Okay, now that is when we're talking about bond polarity, right? Because we can talk about the bond, right? Only the bond. We also have what we call molecular polarity. Molecular polarity is looking at the whole molecule. Okay, so if we were talking about, let's say, carbon dioxide. Okay, now, in this case, if we looked at the bond between oxygen and carbon, right, which is a double bond. Now, this bond, right, is gonna, or I should say, the bond between carbon and oxygen, the electrons are gonna be favoring oxygen, or is it gonna be favoring carbon?
Oxygen.
It's gonna be favoring oxygen because why does it favor oxygen?
Carbon is weaker in electronegativity.
That's right, because carbon is weaker in electronegativity. You go to peak table, we'll see it. Carbon is about 1 less than oxygen, right? So oxygen is going to be pulling the electrons closer to it, okay? Now, in this case, we have an oxygen on both sides of carbon. Okay, so now you got to look at it like this. Have you guys played tug of war?
Yeah.
Okay, so let's say you had twins that were exactly the same strength. Neither of them were stronger than each other. They were exactly the same strength on both sides. And you're in a wheelie chair. Are you going to be pulled towards one of the twins or the other twin, or are you just going to be in the middle?
In the middle.
In the middle.
Okay. So because on both sides of you, you have equal pull happening and they're both pulling out, right? You're not going to move. So there's no polarity to the molecule. So as a molecule, as the whole thing, this guy would have no polarity. So it would be non-polar. Where the bonds, the bond polarity would be polar. Okay, does that make sense?
It does make more sense now.
Yeah,
Okay.
it makes sense.
Mhm.
Non-polar. Okay. Okay, so that's polarity. You guys are feeling it pretty good so far?
Yes.
Okay. So this is just basically showing you that, right? So non-polar, even sharing. This one is polar. Well, here, one is stronger than the other, so it gets the electron the majority of the time. And then this would be ionic, okay? And then I gave you how to calculate those values. You guys remember that table that I wrote down? Where X is less than and equal to 0.4. And X is, oops, sorry, 0.4. X is greater than 0.4, but less than 1.8. And 1.8. Oops. Equal to x. So if x is greater than or equal to 1.8, this guy's going to be ionic or ionic character. This guy's going to be polar, and this guy's going to be nonpolar. And then where x is the difference between bonds. So difference, I should say, between bonding atoms. Okay, so if you're given the electronegativity of oxygen, and let's say we're talking about carbon. So what we would do is, so carbon is 2.55. So we always take the one that has the largest value and we subtract it, and oxygen is 3.44. Okay, and so this would allow me to know the bond polarity numerically, right? So what is that value?
.89.
Okay, so 0.89, where does that fall between? Polar, nonpolar, or ionic?
Polar.
Polar.
Polar. Simple, right? So that tells me the bond between oxygen and carbon is a polar bond, and oxygen is paper. Okay? Everybody got that?
Yes.
Okay. Can you guys see? Okay, good, good. Okay, let's keep moving. Okay, so that's the electronegativity. We've already talked about the electronegativity. You guys are feeling confident in electronegativity?
Little by little.
Little by little.
Can we quickly go over it real quick if you can, or?
Okay, so we've gone over it. It's that table that we just saw, right? And so again, it's just you're using the bond, the difference between the two bonds. So if we look at hydrogen and oxygen. Here's hydrogen, here's oxygen. So 3.4 minus 2.2. What does that equal?
1.2.
1.2. So 1.2, is that polar, nonpolar, or ionic?
Polar.
It's polar, right? Because it's between 0.4 and 1.8. Simple. So then that lets me know that the bond between hydrogen and oxygen favors oxygen. Okay. Are you with me, Catherine?
Yes.
Okay, good. Okay, so this is just showing you again exactly what we just talked about. Okay, we've talked about multiple bonds. We've talked about single bonds. We've talked about double bonds. We've talked about triple bonds. Triple bond is sharing how many electrons?
6.
Okay, a double bond is sharing how many electrons?
4.
4.
Okay, single bond is sharing how many electrons?
2.
2.
Okay. We've talked about center atoms, right? Who's going to be in the center? How do we determine if something is in the center? Can hydrogen ever be in the center?
No.
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 Okay, So we know that, right? So we're like, man, you guys have been on top of things. I've been teaching all this crap and you're like, okay.
And we're doing bad on the exams.
And you're doing bad on the exams. That's because you didn't realize you already knew it. You doubt yourselves too much. You overthink it. Okay, so now that we've talked about the octet rule, we've talked about the exception. We've also talked about formal charges, right? Okay, so let me tell you about some exceptions to the octet rule. If you ever have a molecule that has a total odd number of electrons, like in this case, we have nitrogen and oxygen. Nitrogen monoxide is what it's called. Nitrogen has how many valence electrons?
5.
It has 5. Okay, and oxygen has how many?
6.
6.
Okay, 5 plus 6?
11.
11. Okay, anytime that it adds up to a total of a number that has a negative, an odd number, but if it's an odd number, we know that it will never, ever be able to reach its odd. Okay? If all of the electrons add up to an odd number, it will never, ever be able to reach its octet. So you're going to ask me, what do I do under those circumstances? Right? Can't reach its octet. The rule is the guy who has the strongest electronegativity reaches his octet. The other guy gets as close to its octet as possible, but doesn't go over. You guys got that?
Yes.
Okay. So we're going to try to get as close to its octet as possible. So in the case of nitrogen monoxide, we adjust it so that nitrogen has 7 around it and oxygen reaches its octet. If we had nitrogen dioxide, then we make sure that each of those oxygen reaches its octet, 2, 4, 6, 8, 2, 4, 6, 8, and nitrogen has 7 around it, 2, 4, 6, 7. Does that make sense?
Yes.
Okay. Now, I know you guys are going to want to throw bricks at me here. Okay? No brick throwing here. Okay, so this next one is called hypervalence. I'll spell that for you. Okay, hypervalence is when you have more than 8 around you, right? And elements, I'm going to go to the periodic table, and I'll explain it to you why they're able to do this. It's true. Okay, so elements that are in the 3rd period, all of these guys and anything below it are able to go and do hypervalence. Now, they'll use hypervalence to make stable structures, right? And that are more stable than if they had their octet there, right? And in most cases, they're going to try to do the octet, but if they can't do the octet, they'll make hypervalent molecules, meaning that they'll have more than 8 electrons around them. Those center atoms will. Okay, center atoms could have more than 8 electrons around them. Okay, so let me give you the examples. So all of these guys that are below, that are after the 3rd period, all of these guys down here, these guys can be hypervalent. Okay, where these guys up here won't ever be hypervalent. Okay, are you with me?
Yes.
Okay, so let me show you what I mean. Okay, so here we have phosphorus. In this case, phosphorus has 2, 4, 6, 8, 10 around it, right? Fluorine reaches its octet, okay? So fluorine is kind of a bully. Fluorine is, in most cases, going to make sure that it reaches its octet. It does not like to make double bonds. It always likes to make single bonds. It can make double bonds, but it prefers to make single bonds. Only make double bonds if it absolutely must, right? That's the only time it'll happen, okay? Now here we have sulfur. It has 2, 4, 6, 8, 10, 12 around it. Okay, so sulfur is able to sit there and have an octet more than 8 in this situation. And the reason why it's able to do that is because you have the d orbital now open that you can actually be used to occupy space for electrons. Okay, so you not only have the s and the p, you also now have the d that's now available after the third period. That's why we start at 3d. Does that make sense?
Can you go over it again?
Yeah. Okay, so if you look at this guy, this is the third period, right? Here, this is the 3D orbital, right? So these guys, because they open up that third energy level, now they also have that D that they can put electrons in that they're sharing. So they're able to do that. Before, we only had the 8, right? So here in the 2, you only have 8 because you have the S and the P, because you only have 2S, 2P. You don't have a 2D, right?
Mhm.
So since there's no 2D, we can't use a 2D, right? So you can't put them there. Where these guys, they're in the third period, they open up that third energy level, which also includes these orbitals. And so you can use those orbitals to sit there and do bonding as well. Okay, so you open those up so you can get your quote octet fill, but that means that you can fill up this entire D shell as well, right? And so all of these guys are able to use that d orbital to sit there and fill things up. And that's the same thing with these guys down here, right? So that means that they're able to be hypervalent. They can have more than 8 around them. Okay? Does that help?
Yeah.
A little bit, yeah.
Okay, so then we have these special cases. There's 2 of them. These guys are called hypovalent. Or hypovalence. So in the case of hypovalence, these guys won't reach their octet. They don't want to reach their octet. Beryllium is a metal that has a personality kind of defect. It thinks it's a non-metal, right? And it thinks it's a kind of a weird non-metal that it only likes to have 4 electrons around it. It doesn't want more than 4, only 4 electrons. 2, 4, okay? So beryllium will form covalent bonds. In most cases, metals don't form covalent bonds. They form ionic bonds. But beryllium, for some reason, it's like, I am not like the rest of those metals. I'm something special. And I only want to have 4 bonds. And we've got to share. I don't give up, you know? Okay? So beryllium will have 4 electrons around it. So it will have 2 attachments. Okay? Does that make sense? Or should I say, do you understand that exception?
Yes.
Okay. The next exception is boron. Boron likes to have 6 around it, right? It doesn't like to have its octet full. It only wants to have 6 around it. And boron is kind of, again, another weird case because boron is a metalloid. And so it's kind of using the aspects of the metal and the non-metal and so, okay, I'm just going to be weird, you know? So it will only have 6 electrons around it. Okay, so it will never reach its octet. Okay, are you with me?
Yeah.
Okay,
Yes.
and then I'm supposed to mention oxygen can sometimes make things crazy. And so you'd end up having molecules where you have like 5 oxygens around it, and that would cause things to be hypervalent and stuff like that. Okay. So certain compounds with oxygens will screw up our octet. Okay, so the last thing that I want to talk about, and I know we're over time, is metallic bonds. Metallic bonds are bonds between metals. And the way that they work is that metals, because metals in most cases want to be charged, positively charged, what they'll do is they'll delocalize their electrons. So what they'll do is sodium. You know that sodium has 1 valence electron, right? True? we know that sodium wants to be like who?
Neon.
It wants to be like neon, right? So it wants to get rid of that one electron. So what it'll do is it'll say, okay, I'm going to go ahead and just drop this electron on the ground right next to me and pretend that it's not on. And hopefully somebody comes by and picks it up. Okay. So then the next sodium molecule does exactly the same thing. And then the next sodium molecule does exactly the same thing. Okay, so you got a positive, and then that electron acts like it's a negative. And then you got a positive, and then that electron acts like it's a negative. And so if you have the sodium surrounded by a pool of negative charges, which are the electrons, and the sodium is positive, you get like what we call those lattices forming, right? So they kind of act as if they're kind of ionic with each other, even though that electron really belongs to sodium. So it's kind of keeping it together. Does that make sense?
Yes.
Okay, so that's essentially what's happening in the case of sodium. So in the case of magnesium, magnesium has to get rid of 2 electrons to be like neon, right? And then when it does, it'll go 2+, and then it'll get rid of 2 electrons. And then the next magnesium will do exactly the same thing. But it's not, you know, it's just delocalizing it temporarily. It's keeping it somewhat close because it needs to interact with it, right? Okay, now because of this, we're able to form what we call alloys. So I can mix metals together, and then they make one new metal, right? You guys, how many of you guys have gold? Anybody have gold? Well, let me show you a picture of this ionization, of the delocalization. Okay, so this is what it looks like in theory. Okay, you guys, does that help see it?
Yes.
Okay, so how many of you guys have gold? Anything gold? Anybody? Anybody got bling? What was that?
Are you saying gold or coal?
Gold. As in gold. I love gold.
Yeah,
You have gold? You have a gold ring?
not on me.
Not on you? Is it 24 karat gold or is it 18 karat gold?
No, it's 24 karat. Well,
24 karat. So it's 100% gold.
yeah.
Okay. So anybody got 18 karat gold? Yeah, I have a tendency of losing jewelry. So when I buy jewelry, it's always like, you know, 5 karat gold or, you know, so it just has that gold plating on it, you know, gold plated. I have a gold tooth. Okay, Nate, let's talk about your gold tooth. Is it 18 karat gold? 24, oh, it's all gold. Okay, it's soft and smushy. Oh man, super soft. Man, that's crazy. See, I'd probably again go with the lower part, you know. Okay, so alloys are essentially gold. Alloys are essentially metals that are mixed, right? So 18 karat gold is basically, it's going to be 75% gold, 12%, 12.5% silver, 12.5% copper. Okay, and so, and what it does exactly the same thing, where it actually will delocalize the electrons so that it acts like it's positive and negative charge, and you're just putting different metals in there. Okay, so these wouldn't all be sodium; they would be, in this case, would be gold, silver, and copper mixed in together. Okay, and they stick together. It makes the metals sometimes stronger. Like if you guys 18 karat gold versus 24 karat gold. 24 karat gold is kind of soft, more malleable, where 18 karat gold is a little more firmer, right? Okay, so these are some examples of some of the alloys that we come into contact with, right? And just the concept of using that metallic bond to sit there and make these alloys. And it changes the characteristics of the metal, right? The bronze behaves different than the copper and the zinc independently. It looks different as well too.
No what?
Bronze. Bronze. Bronze, bronze, bronze. I'm sorry, copper and tin. And the brass is different than the copper and the zinc. Okay. Okay, questions, concerns, Cash?